All right, today we're diving into one of the most powerful tools in all of science and engineering, mathematical modeling. Seriously, this is how we create a digital blueprint for reality itself. It lets us see how something will work before it even exists. Let's get into it.
So think about it. You're designing a brand new jet engine or maybe some revolutionary new metal. You can't just build 1,000 different versions and hope one of them works, right? That would be crazy expensive and would take forever. So how do you test, predict, and totally perfect something that's still just an idea on a computer screen?
Well, the answer is a mathematical model. And no, this isn't just a boring page of numbers. It's a living, breathing digital blueprint. What we're doing is translating a physical system, like that jet engine, into the language of math. Once we've done that, we can simulate its behavior, push it to its limits, and predict how it's going to perform under any condition we can dream up.
So, how do you actually build one of these digital blueprints? Well, it turns out that pretty much every mathematical model out there, whether it's for predicting climate change or simulating a car crash, is built from 3 essential ingredients. Think of it like a recipe.
The very first ingredient you need is the set of governing equations. This is basically the universal rule book. You know, the non-negotiable laws of physics, like conservation of mass, momentum, and energy. No matter what we're modeling, it absolutely has to obey these fundamental rules. Whoa, okay, I know what you're thinking when you see an equation like this one. It looks pretty intense, but don't get hung up on the symbols. The idea behind it is actually something we all understand. This is just the law of conservation of momentum, and it's simply saying that everything has to balance out. All the forces pushing and pulling inside a material, plus any forces acting on it from the outside, have to perfectly equal the material's own motion. It's like the universe's ultimate balancing act, just written down in math.
But, that universal rulebook isn't quite enough. We also need our second ingredient, constitutive relations. This is what defines the material's unique personality. Is it stretchy and bouncy like rubber, or is it super stiff like steel? Does it get hot really fast like copper, or does it stay cool like wood? These equations tell the model exactly how a specific material is going to react to things like forces or temperature changes.
A super common example is Hooke's law. It gives us a really simple, direct connection between stress, which is the force you're applying, and strain, which is just how much the material stretches or squishes. Essentially, this little equation gives our model the precise personality of something elastic, like a spring.
And our final ingredient is what sets the stage. These are the boundary and initial conditions, and they basically define the system's environment. The model has to know what's happening at its edges. Are they being heated up or held perfectly still? And it also needs a starting point. What did the system look like at the very beginning of our simulation?
Let's just make sure we're clear on the difference here. Boundary conditions are all about the space around the system. Think of them like the frame around a picture. They define what's happening at the edges. Initial conditions, on the other hand, are all about time. They're the very first snapshot of the system, right at time 0. You've got to have both to get a single accurate answer.
Okay, so we've got our 3 ingredients. Now what? How do we actually put them all together? Well, let's walk through the 5-step recipe that engineers and scientists use to build a working model from the ground up.
And this process makes so much sense. First, you define exactly what it is you're studying. Then, you grab your rule book, the governing laws of physics. Next up, you define your material's personality using those constitutive relations. After that, you set the environment with your boundary and initial conditions. And finally, once all of that is in place, you solve the model.
Now that last step, solving the model, it's almost never simple. For any real-world problem, these equations get way too complex to solve with a pencil and paper. That's where computers become absolutely essential. Scientists use powerful techniques, like the finite element method, to chop the big problem up into thousands of tiny manageable pieces that a computer can then solve one by one.
I know this might still feel a little bit abstract, so let's make it real. We're going to take this exact recipe and apply it to a super common engineering problem, simulating what happens when you weld a metal plate.
The goal here is pretty straightforward. We want to predict exactly how heat is going to flow through this metal plate when a welder hits it with an intense focus torch. And this is so critical for understanding how to prevent things from breaking or warping.
And look at this. See how perfectly our ingredients map onto the problem? Our rule book is the heat equation, which is really just a version of the law of conservation of energy. The material's personality is defined by its specific properties, like thermal conductivity, how well it carries heat. And the environment is set by the plate's starting temperature and, of course, the intense heat coming from that welding torch.
So why would we go through all this trouble?
Well, look at what the model gives us. We can predict not just the temperature at every single point at every moment in time, but also the dangerous stresses that build up as the material heats up and cools down. This lets us perfect everything from welding techniques to 3D printing, making sure the final product is as strong and reliable as possible.
And here's the really incredible thing. This 5-step recipe is totally universal. You can use the exact same thought process to model how a car body crumples in a crash, or even how tiny, damaging hydrogen atoms can sneak their way through the steel of a massive pipeline. The specific ingredients might change, but the recipe itself always stays the same.
So, let's zoom out. What's the big picture here? Why is mathematical modeling so ridiculously important to modern science and technology? Let's wrap this up.
And this really gets to the heart of it. Mathematical modeling isn't just another tool in the toolbox, it is the absolute foundation. Every single simulation, every digital twin, every piece of software that predicts how the physical world works, it all starts with a mathematical model, period.
And having this foundation gives us something of a superpower. It lets us ask, what if, 1,000, even 1,000,000 times, without ever having to build a single physical thing. This completely changes the game for research and development. We can move from a slow, expensive process of trial and error to one that's lightning fast and predictive. It just accelerates innovation, cuts down on waste, and lets us design and build things that are safer, stronger, and more efficient than we ever could before. This leaves us with a really fascinating thought to end on. For centuries, we've used math to describe the world we can see around us. But now, our models are getting so good, so predictive, that they're helping us design a world that has never even existed yet. That digital blueprint we talked about at the beginning, it's not just a copy of reality anymore. It's becoming the architect of our future.